Well, Newton did a great number of things in his time. For high school students, one of his most famous contributions is what we call Newton's laws. And these basically describe how forces interact and how forces create motion. There are three laws of motion and the law of universal gravitation. And in this video, I will describe those four laws and the nuances connected to them. In subsequent videos, we'll be doing how these laws how they actually are applied and how we make calculations. So Newton's first law is known as the law of inertia. Now this law really doesn't exist. As you will see, it is really just a special case of Newton's second law, but it's been around for 300 years, and so we continue the myth of it being a unique principle. If an object's at rest, first off, an object's velocity will not change unless acted upon by an external force. Now let's remember when we deal with vectors. A vector is both a magnitude and a direction. And so for the velocity to be constant, the direction and the magnitude must both be constant at all times. If the object's speed changes, that's acceleration. If the object's direction changes, that is also acceleration. And that is a harder concept for young people sometimes to appreciate. The easiest one is to see that an object at rest will stay at rest. If an object at rest has some kind of explosion or some kind of separating force, the particles will move apart, but the center of mass will stay in exactly the same location until acted upon by an external force. That is the main point here, okay? An external force. If we have an object in motion, it's fairly easy to see that for this object to change its direction, you have to push it. Okay, it has to come from an external force. If it slows down or it speeds up, it's also going to require an acting force. Now, one of the things that we have to be careful of when we study this subject, whether we do it just by observation of our natural environment or we're doing it, for problem sets and so on, is to make sure we understand when the force is external and when it isn't. An external force is drag, for example. So let's suppose we have this situation where things fly apart, but you have some items that are more susceptible to drag than others. Then it looks like the center of mass moves, and this would appear a violation. But of course that's not true because we have an external force in this example called drag. So one of the things that's important when you look at a question is to pick it apart and make sure that you can understand what is an external force and what is not. So once again, the law of inertia, and historically, depending on who you talk, we think that Galileo probably understood this concept, but Newton certainly formalized everything in his 1687 Principia, which picks up these three laws plus the law of universal gravitation, which we'll be talking about here in the next little while. And one of the most famous principles of Newton that high school students encounter is Newton's second law. And this is defined by the equation the force is equal to the mass times acceleration. But within this, there's a whole bunch of hidden meanings that I don't think are often explained very well. So I'd like to do that for you today so that we understand what this equation truly means. The force that we're interested in is what we call the net force. And what that means is it is the vector sum of all acting forces. So we could have 50 forces acting on an object from different directions, different magnitudes, and what have you, and we add them up in a legitimate vector way. So you've seen enough of my previous videos. We would add them component-wise to obtain a net force, which is the force that is here. The acceleration that is described here is the observed acceleration. Sometimes people will say, well, each force has an acceleration, we add them together. That's not true. There's only one acceleration. That's the one that actually occurs on the object. But the important point is to recognize that that's what this means. The acceleration we're talking about is the observed acceleration of the mass m. Now, we might be able to know this and say, okay, well, what are the forces? Well, we could tell you from this, we would tell you what the net force is. But we're not going to be able to tell you all the other smaller forces. That's lost, okay, in that situation. So it's very important that we look at this. Something else that needs to be remembered is that, that this is a scalar multiple. So the force, the net force, is parallel to the resulting acceleration. Okay? M here is a scalar, and thus will not change the direction. Also, in our current understanding, mass is always taken as a positive. So therefore, the force direction and the acceleration direction will always be in the same. So if we create a force, a net force, and we throw the ball will go in the direction of the force that we exert, which is what we expect. Okay, but this proves or requires that from the mathematical standpoint. So really important to remember what this means. Physicists are often like to leave things out, almost like it's some kind of a, you've got to understand what we're doing kind of thing, these are the things that are left out. So again, this is the net force. By that we mean the vector sum of all acting forces. So it depends on the dimension. Are you dealing in 1D, 2D, 3D? And if so, what does it mean to take a vector sum? Okay. And obviously your acceleration will be in the same dimension as the force is. So if we're in 2D, your acceleration will be a 2D vector, and so on. We treat everything the same. Now we'll be doing problems in the next videos related to forces and all the rest, and this will become clear. But this is just the introduction to give you the specifics of this. I mentioned in the previous video segment, the previous panel, that first law is really a special case of second law. So we say in first law, an object will retain its velocity unless acted upon by an external force. Well, let's think about that. If an object is retaining its velocity, then the acceleration by definition has to be zero. If the acceleration is zero, that means the net force is zero. As soon as the net force is non-zero, the acceleration becomes non-zero, and therefore it acts. So this is really just a special, so you can see that first law is really just a special case of second law that's verbalized. And then we come to Newton's third law, which is probably one of the more misunderstood laws in physics, for young people especially. And this is the action equals reaction law, which is just Old English for force. There's an equal and opposite force acting at all times. The problem is that if you say that, you say, well, gee, if that's the case, why does anything ever move? How could we ever get an imbalance of forces to cause an acceleration? And the answer is in the definition. We have the force on A due to B. Here we have the force on B due to A. So in other words, these two forces are acting on different objects. And that's what gives us so these two forces act on different objects. Now the best way perhaps to illustrate this is by an example. So let us consider an example here of a balloon. We have a balloon that you would have, you might have at a party, and it's tied off. The balloon is solid, and the force of the pressure of the air inside is acting in all directions the same. And we know that because it's a fluid, and that's how they behave. However, if we take the knot out of the balloon and we open the throat slightly, we end up with a different situation. And we all know that if we let this go, the balloon will fly off across the room. So let's look at why that happens. We can see here in the up and down sections that we have equal forces. It's not going to change. The difference comes where we have this force here pushing against the front of the balloon, and the force in the opposite direction, which last time was pushing against the knot, is now pushing the air out of the balloon. This force is pushing on the balloon, and this force is pushing on the air. They are equal in the sense of their magnitude, but the problem is now there's an unbalanced force on the balloon because there's no force pushing on the balloon that opposes this one. And then the balloon then has a unbalanced force in this direction, and the balloon will move off. Okay? The air in the balloon was static before. You open the throat up and you let the balloon go. The force in the balloon will push the air out at quite an aggressive rate and accelerate it. So this force is acting on the balloon. This force is acting on the air, on the exhaust. Now this is exactly the same principle that we use for aircraft engines, that are the jet engines, and rockets. Now there are different ways to achieve this, but in the same effect is that if you have a balloon at a party, the balloon doesn't go very far and it dies because the amount of air in it goes down to zero and you end up with just a limp balloon again. If we're going to have travel, we need to maintain this pressure. So we have to invent fancier devices that will maintain the pressure that's appropriate to give us this unbalanced force in a controlled way. And this is true in aircraft engines, which use compressors and combustion to produce a particular amount of imbalance. And in the case, the more advanced case, of course, is rocket engines, which have more of an obvious thrust chamber where you have a profound force going. The difference is with rocket engines is that they only last for a few minutes, whereas aircraft engines live within the atmosphere and we can go on for hours. But the principle of either of those technologies is exactly the same as the principle of the balloon at the party. In Newton's creative period, when he was sent home from Cambridge to avoid the Great Plague of 1665-66, and he was back at his mother's home in Woolsthorpe, and I'm sure given his personality difficulties with his stepfather and his mother, this couldn't have been all this a fun time for him. But nevertheless, he had a very creative period, and famously the idea was that he noticed apples falling from the trees in his mother's apple orchard, and recognized that there was a force that pulled these apples to the surface. He deduced that the moon was held in place around the earth by the same force. Now this was a leap of intuition that had not been done in the past. Kepler, however brilliant a mathematician he was, came up with his 3 laws of planetary motion in 1608, 1609, fully, almost 60 years earlier, which were perfectly valid, but could not connect what the central force was that caused everything to work as well as it did. Sometimes it just takes that piece of intuition. Newton then decided to figure out this relationship of how gravity affects not just local objects, but astronomical ones. And it's a natural connection to go from the Earth to the moon, and then from the Earth to the Sun, and that the entire solar system is controlled by gravitation. And so he arrived at a relationship, which we'll describe in the next panel. So what Newton realized was first that the force of gravitation was proportional to the product of the masses divided by the square of their distance. And he called it the law of the inverse square. To make this an equal sign, we need a constant. And this constant is the universal gravitational constant. Has a value of 6.67, depending on who you talk to. There's 0.24 when I was younger, but we'll leave that for now. Times 10 to the minus 11. Okay? And then it's meters cubed over kilogram seconds squared. We always get these silly units when we get constants. But nevertheless, this gives us an equality. The negative sign is there because gravity is always an attractive force. The masses attract each other. We don't, at least in everyday experience, we don't know of examples where it is not. When you see this equation, you will often see M1 and M2. However, my background is more in astronomy. And what we realize in astronomy is that we need a really big mass for gravity to have any effect at all. A planet, a star, or something like that. Even a mountain does not provide anywhere near the gravitational force we need. One of the probes that they sent to one of the asteroids, it actually had to have claws to connect in to the asteroid itself to hold itself on the surface. So we need something pretty substantial. In the case of Earth, we're looking at roughly 6 times 10 to the 24 kilograms. That's a an example. And then we have the other mass that's being attracted, divided by the distance between their centers. And this is something else that maybe we need to remember, is this is between centers, not from the surface. And finally, we have this little unit vector here. The masses are scalars. This is a distance and this is a constant. So this whole thing is a scalar. But this is a force, and it's a vector. So this has to be a vector. So what we do is we take the magnitude of this vector, and we take a unit vector here, which we've talked about already, and it acts in the same direction. Okay, this is a vector of length 1 that is lying between these two masses, between their centers. Okay, and this is the formal version of it. Now, something that will happen perhaps in university is you will get a professor or an instructor who's something like this, who may, on occasion, play a little game with their students. And so I'm going to reveal this to you now so that you don't get caught in this. You might see r cubed r. But r is equal to r times r hat. So this is really minus g big M small m over r cubed times r hat. And you cross out one of those and get back to the other case. But it is natural for young people, when they first see this, not being comfortable exactly with the notation, putting their hand up and making themselves appear foolish. So you might want to be careful of that, and this is why the basics, the background of all these ideas are something that I stress when I teach my students, because it's really important to know what this all means at this basic level before we get into the fancy stuff. So there you have the basic explanation, I guess, of Newton's three motion laws plus the law of universal gravitation. Hopefully this made you aware of some of the nuances of it, and now we can go forward and look at solving some of his problems. Thank you very much for watching.